Hi, welcome to lesson 4 in the online tutorial series on digital signal processing using MATLAB and Python. You can also visit us at www.jcbrolabs.org if you want to download the source code and the document file of this lecture videos. Further, we also provide online tuition classes for engineering subjects like DSP, control system, and other electronics and electrical related subjects. So if you are interested, you can contact us at jcbrolabs@gmail.com, or you can fill the form available on on our website. Okay, so in this video we'll move forward with the digital systems, like the representation of the digital system and the solution of digital system, and we will do some numericals prior to moving forward. Okay, so let's start it. So we will do some numericals after that. Okay, so let's start. Before in the last video we talked about an LTI systems, right? So an LTI system which can be represented as this one, like x of n, not h of n, represented by h of n as impulse response, and output was y of n and the input was x of n. Okay, so there are several ways to interconnect this system. Suppose we have more than one system, so there's some topic like the system interconnections. So how we are connecting different systems, different subsystems to make a one big system. So for system interconnection, first in the series we have this cascade connection. So what happens in cascade connection? Suppose we have a system which has the impulse response as h1 of n, and we connected in series with the another system, that is the h2 of n. This is as yn, and let's say this is a x of n, and this signal will be the intermediate signal, or we can say an intermediate signal, this z of n. So this entire system we want to represent it by a single system. So this entire system can be represented as we discussed, the output was the h of n convolution with h of n, x of n. So here we have two systems, so it will be h of n convolution with h2 of n, and this one will be the output as y of n, and this one will be the input as x of n. Okay, so we will this is the first connection. Second interconnection scheme like this parallel connection. So in parallel connection we have two different systems, say h1 of n, and we connect them in parallel like h2 of n, and the output of these two systems can be go into the adder or the subtractor, so which can be, that can be represented by plus or minus sign, or let's say it goes into the adder, so there will be a plus sign. If it is going into the subtractor, another sign could be the minus. So this is x of n, and if we want to represent it by a single system, then this will be simply h1 of n plus h2 of n, and this one will be y of n, and it will go inside to x of n. Similarly, there is another kind of system, and which is more often used for recursive kind of modeling, and that is known as the feedback connections. So in a feedback connections, let's say we have forward transfer function which is represented by x of n, and the output of this, the same system, goes into the input of another subsystem, and the output of this another subsystem gets subtracted more often. Only then it will be a negative feedback. If we provide a positive feedback, the system may become unstable. So it goes into negative, and then there could be like x of n, the input, and then this y of n. So there are several expressions for these two systems which we can further study when we'll be studying this Z transform. Okay, so this is more often system feedback connection is used. So any typical system, if we talk about, or a big system, will be a simple combination of these three types of connection. That will be either cascade, parallel, or a feedback connected. Okay, so now let's move forward with the topic that was the system representation. So as we give a hint in our last video, like this digital system can be represented by difference equations. So here we will talk about it in detail. As you know, this digital system can be represented by a difference equation. So general form of this difference equation can be right like especially again for LTI systems. So for LTI system, it will be like linear constant coefficient difference equation. Linear constant coefficient difference equations. So it will be LCCDE. So it can be right like k from 0 to n, let's say, and d of k into y of n minus k, and equals to, let's say, k equals to 0 to m, and then p of k into x of n minus k. Okay, so this is the general representation of a LTI system in the form of a linear difference coefficient equation. Now this p of k, they are general terms which is we should be familiar with. This p of k coefficients are known as the numerator coefficients. Okay, and why these are called numerator coefficient, we will go into the detail in Z transform lecture. And then this d subscript s is known as the denominator coefficients. So we will be using these terms when we'll be dealing in the subpart of in MATLAB or Python programming. We will be referring these coefficients as denominator coefficients and the numerator coefficient. So if we take an example and say, let's say capital N is equals to 2 and capital M is equals to 3. So our this linear difference equation simply will be like d of 0 y of n plus d of 1 y of n minus 1 plus d of 2 y of n minus 2, and this will be equals to like p of 0 x of n plus p of 1 this x of n minus 1, then p of 2, that will be x of n minus 2, right? And because m is 3, so it will be one more term will be there, p of 3 x of n minus 3. So this is the general representation of this complex equation. Now if we talk about the solution part of it, like solution of difference equation. So this solution of difference equation, ultimately what is our objective? Our objective is to find the value of y of n, right? So y of n should be some function of x of n. So we want this kind of solution from this differential equation. Like for time domain differential equation, we want to the expression of y of t in terms of t or xt, right? So that is our case. In our case, this x of n could be varying. Okay, prior to that, this solution y of n can be thought of as a two part of the solution, which is known as yc of n plus yp of n. Here this YC of n is known as the complementary solution. Complementary solution, or it is also known as the homogeneous solution. It is calculated when x of n is equals to, by putting this x of n equals to 0. That means it could be also referred as the natural response of the system, because we said yn was the response of the system. So if we put x of n equals to 0, that means there is no input to the system. Even then, if we are getting some output, that is known as the natural response of the system. Similarly, there is another term also, that was the yp of n. That is known general term for it, the particular solution. Okay, particular solution resulting from, that means if we have applied some input, then what solution, what response we are getting, that is known as the yp of n. Or it is also known as the forcing, it is also known as the forced response. So forced response means we have applied some input like this x of n, and we have forced the system to provide some output for this specified input signal. That is why this yp of n is also termed as the forced response, and this yc of n was the natural response, because we applied this x of n was the input signal. So there are several ways to find the solution of this yc of n and yp of n in discrete domain, like you used to calculate in time domain, or you have done this from your basic mathematics, engineering mathematics course. So we will not go into the detail of this solution, because we will be solving such equation using Z transform, and we have not introduced that Z transform yet. So we will be dealing with the solution of this equation in the later. But these terms should be kept in mind, like yc of n, complementary response or the natural response, and this yp of n, the forced response of the system. Okay, so now moving forward, one more thing, if we put this x of n as an delta of n in our previous equation, that was in equation this one, if we put this x of n as delta n, so this we know y of n is known as the h of n. So we can also write like equation delta h of n plus d1 h of n minus 1 plus d2 h of n minus 2 is equals to similarly that was p0 delta of n plus p1 delta of n minus 1 and so on. Okay, so if we solve this equation for h of n, then we can find the impulse response of the system. Okay, so there was some other classification of the LTI systems as well, like was the based on the impulse response, like FIR system, that is the finite impulse response system. So in our case, if the impulse response, this h of n, is of finite duration, that means it exists from 0 to, let's say, n length, and n is less than infinity, then the system whose impulse response is finite is known as the FIR system. Similarly, we have another system, that is IR system, or is also known as the infinite impulse response system. So in infinite impulse response system, Hn goes from 0 to infinity. That means if this n is equals to infinity, so we have an infinite sequence or infinite numbers in the output response. Then this system whose h of n has these infinite terms are known as the IIR system. Similarly, we have based on output calculation process, like non-recursive systems. So non-recursive systems. So non-recursive system means in which the output depends on the present or past values of the input only. depends on present and past values. For example, we can have this y of n is equals to, let's say, k equals to 0 to m, and let's say p of k into x of n minus k. Similar equation which we just represented in terms of LCCDE. So here this y of n is depending on the present and the past values of x of n. So this kind of system is known as the non-recursive system, or generally we have another term for such kind of system like moving average model. This is also known as the moving average model of the system. And if we also represent it, it also forms the FIR system as well. In this case, this, if this m is less than infinity, this will form an FIR system. Okay. Similarly, we have another kind of system. Those are recursive in nature. So there could be two kind of recursive systems. Like general definition for recursive system is if our output depends on the present and past values of the input and on the past values of the output as well, then it is a kind of recursive system. That means output is being fed to the input as well, a kind of the feedback system we talk about. So there could be a two combination of these systems. Let's say one kind of system could be y of n depends only the present value of the input and past values of the output. So let's say k equals to 1 to n and d of k into y of n minus k. So here what is happening, this y of n depends on the present value of the input and it has been subtracted from the past values of the output. That is a kind of a feedback system, negative feedback system. So such kind of systems, also the recursive system, and especially this kind of model, are known as the autoregressive model. So this model represents the autoregressive models of this, and it forms an IIR kind of system, and we will learn why this is IIR in upcoming videos. Similarly, it could be like our output is depending on the present input and past input and the past outputs as well. That means all the combination of the previous three. So let's say for k equals to 0 to m, p of k into x of n minus k, and then minus summation of k equals to 1 to capital N d of k into y of n minus k. So in this case it is depending on the present and past values of input and the past values of output. So it is also an example of recursive system, but in this case it is known as the ARMA model. ARMA, that means auto-regressive moving average model. So a combination of the previous two models, like this was the moving average MA and this was auto-regressive, and the final one, this is the ARMA model. Okay, so this is about the systems again, how to represent such the system, and what are the several other classifications of the system. So let's take a small example of the system related to the stability, like what kind of questions generally comes if you are preparing for some university exam and so. So let's we will also start a new series. We have also started a new series like numerical analysis on DSP. So in that series we will be dealing with numericals only, which occur with these digital systems. Okay, so let's say we have an example, say y of n is given by a times x of n minus 7. So the question is find whether it is a stable or not, or you have to find b-boy stability of the system, whether this system is a b-boy stable or not. So from our previous class, we know our system will be b-boy stable if this mod of h of n is absolute summable. That means that is a less than infinity for bounded input signal. So let's say impulse response means we have applied x of n as the delta signal. So in that case this y of n will be our h of n, right? So it will be a into del of n minus 7, right? So del of n minus 7 means if we write it like, or if we plot it, it is equals to a when n is equals to 7 and it is 0 when n is not equals to 7. That means it exists only on at n equals to 7 and the value is corresponding to a only. Okay, so if a is less than infinity, because it was the bounded input signal, so if a is less than infinity, then obviously this signal is the Bibo stable and its summation will be simply equals to a, which is always less than infinity. So this system is a Bibo stable system, or we can say this h of n is the absolute summable. Okay, like similarly there could be another example, simple example we'll say, like this h of n is equals to 2 to the power n into u of n. So this power, so by looking at it, it seems to be unstable because it is increasing with time, but we need to prove it through mathematics. So let's say from n equals to minus infinity to infinity mod of h of n. Okay, so because u of n exists for the positive values of n including 0, so this summation will reduce to 0 to infinity, n equals to 0 to infinity, then 2 to the power n, right? And this, if it is going to 0 to infinity, so think about 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3 plus so on, and it is becoming an infinite series. So obviously if we sum them all, it will become an infinite number, right? So that is why this is a unstable system, or we can say this h of n is not absolute summable, and the system will be unstable system. Okay, let's just take last example, and the rest of the example will done in the another video in numerical analysis. Let's say simple one, or a simple equation. Let's say y of n is given by a times x of n plus 1 plus b times x of n minus 1. So if we look at this, this system is non-causal because it is depending on the future values of n. But let's do it. We will assume x of n as the delta n signal, that is impulse response kind of thing. So this h of n will be a into delta of n plus 1 plus b into delta of n minus 1, right? So if we write it like if n equals to 0, okay, for n equals to 0, this h of 0 will be simple 0, because it will be delta of 1, a into del of 1 plus b into del of minus 1. So it will be, both will be zeros, right? So h of n will be 0 at h of 1, that means n equals to 1. This one will be b only, and then because ultimately only this signal will have some value. Similarly for n equals to 2, let's say, so it will be a into del of 3 and plus b into del of 1. So again this h of 2 will be 0, and if we take n equals to minus 1, so h of minus 1 will be a into del 0 plus b into minus 2, and that will be simply a. Okay, so if we make a graph of it, so h of n has two values only, right? This is x of n and here n, and let's say this is 1 and this is -1. So here its value is b and here its value is a. Okay, so now we can say if we make us absolute summability of this equation, okay, for let's say n equals to -infinity to infinity mod of h of n, right? So it will be simply, because we have to sum all the sequences, it will be simply a plus b, right? So it will be absolute summable if a and b both are less than infinity. So this term will be less than infinity, and then this h of n will be absolute summable. So the system is stable. Okay, so that's let's stop, and we'll dealing with more numericals in the another videos. Okay, so that's it for this video. So if you like this video, please like and subscribe if you want to keep learning from the free videos like this. And if you want to download the PDF file of this video, then you can visit us at www.jcbrolabs.org. Okay, so that's it for this video. Thank you.